Every time a classifier or a language model learns, something has to tell it how wrong it was in a way it can actually improve from. That something is almost always the same function. The loss we reach for by default when we train these models measures the distance between what the model predicted and the truth. Today we are unpacking that loss, why it punishes overconfident mistakes so harshly, and why it fits language models like a glove. Let us dig in. So to see why this loss is the one we use, compare it against the obvious alternative. Accuracy just asks a yes or no question. Was the top prediction right or wrong? That is great for reporting a final score, but it is useless for training. It is flat. If the model was almost right or wildly wrong, accuracy reads exactly the same, so there is no slope for gradient descent to follow and nothing telling the model which direction to move. This loss gives you a smooth, informative signal instead. It looks at the actual probability the model assigned to the correct answer and turns it into a penalty that shrinks as confidence in the truth grows. Now every prediction has a gradient, a clear direction to improve, which is exactly what training needs. Now, let us walk the computation once from raw outputs to the number we backpropagate. Everything starts with a probability distribution. The model produces raw scores over all the classes, and softmax squashes them into probabilities that sum to 1. So instead of arbitrary numbers, you now have a clean guess of how likely the model thinks each class is. Then we look at just one of those probabilities, the one the model gave to the true class. If the right answer was cat, we ignore everything else and read off exactly how much probability landed on cat. That single number is the whole story of whether this prediction was good. Here is the clever part. We take the negative logarithm of that probability. If the model put 99% on the truth, the loss is tiny. But if it confidently put 1% there, the log blows up and the loss is huge, which is why confident wrong answers get punished so hard. Finally, we average that loss across the whole batch and backpropagate it. The gradient flows back through softmax, and because those two pair together, the math simplifies beautifully. Minimize this over and over, and the model learns to be both correct and honestly calibrated. Strip it down, and 3 ideas carry the whole loss. Negative log of the truth. The loss is simply the negative logarithm of the probability the model assigned to the correct class. So getting the right answer confidently drives the penalty toward 0. Harsh on confident errors. Because the logarithm explodes as the probability of the truth approaches 0, being sure and wrong is penalized enormously, which pushes the model to be well calibrated. The universal default. It is the standard loss for classification, and since predicting the next token is just classification over the vocabulary, language models train by minimizing it too. Perplexity is simply its exponential. All right, let's lock in the essentials. This loss measures the distance between the model's predicted probabilities and the true label, and it is what we call cross-entropy. It is the negative log of the probability given to the correct class, so it stays small when the model is confidently right. Because the log explodes near 0, confident wrong predictions are punished heavily, pushing the model toward calibration. It is the standard loss for classification and language modeling, pairs cleanly with softmax, and perplexity is just its exponential. Want more AI concepts explained in plain language? That is exactly what we do over at Standarity.com. See you there.